Okay, so once more, we have this equation from basic kinematics. We have this equation from basic kinematics. We have the definition of acceleration. And we could put arrows over this and this. And we can have arrows here and here, but we can't have arrows in this equation because we have squared velocities. We have to go into dot products and so forth to do this in vector format. And it turns out it's a scalar thing. Kinetic energy, so okay, if we substitute the F over M for A, we get this and this. And we rearrange the equation. Now, I'm not going to go through the steps of rearranging it. Your algebra is more than sufficient to rearrange this. We get Ft equals mvf minus mv naught, and these can be vectors. We get F delta S equals 1/2 mvf squared minus 1/2 mv naught squared. These are familiar. Okay, we just had a test where we had to use all this stuff. So this is your definition of kinetic energy. This gives you your definition of momentum. Now I'm kind of glossing over the Ft is the change in P, but that's what it is. If P is defined to be mvf minus mv naught, then this product of Ft is, in this situation, your change in P. There's your momentum. And then the other thing, the other big deal is, I'm going to magically insert a delta here. It just comes out of the integral form of the derivation here. And I like to use a delta for this t. I bet your book doesn't, so I chose not to. If I put a delta in here, we get a delta here. And it's perfectly okay to put a delta there. The book uses a J for this. If you have a variable force, then you have a variable acceleration, but with a little integration and a little bit of calculus, you can verify that since the integral of a quantity over an interval is the average value of the quantity over that interval, we can replace this F with an F average, and we can have this officially J is the integral from initial to final time of your function, visualized as the area under a curve, which you can see very well in your book and in the web assigned problems that you might or might not have done. So here we have our more or less entire definition of impulse. So kinetic energy is what you get essentially when you integrate your force over with respect to distance. Impulse is what you get when you integrate your force with respect to time. And they have different results. Again, your work, which is what you get when you integrate your force over distance, is a change in kinetic energy, which goes as the square of velocity. And your impulse is where you integrate your work over time, and it's the it depends on just the velocities. Also, the velocities are vector quantities, which means that for example, your momentum could be broken into components. Pxi plus Pyj plus Pzk if we go into 3 dimensions. Okay, since your impulse is equal to your change in momentum, if you have 2 colliding particles, so let this be M1 with velocity V1, let this be a mass M2 with velocity V2. What happens when they collide? Now let's assume for the moment, just for simplicity, that this collision occurs in 1 dimension. These particles are both moving along the same line and they hit head-on, so that if they rebound still along the same line. Okay, well, when the 2 particles are in contact, they kind of smush each other a little bit, like this, and then they rebound. So you have this elastic, partially elastic, or maybe even totally inelastic, smushing together. If they don't rebound, they stay smushed together. If they rebound, of course, they rebound back with some relative velocity. Okay, so you have if you isolate this particle, it experiences a force which I call F12. This is particle 1. This is the force exerted in particle 1 by particle 2. If you isolate the force on this particle, we'll call it F21, the force on particle 2 exerted by particle 1. By Newton's third law, implies that these forces are equal and opposite. Since the forces are equal and opposite, and since the forces act for exactly the same time, while this particle is exerting a force on this one, this force acts. And while this particle is exerting a force on this one, this force acts. It's an action-reaction pair. It lasts for exactly the same length of time, for exactly the same interval of time. Okay, so it follows that the impulses are equal and opposite. These are the forces exerted, or these are the impulses due to these forces. So if there are no external forces, okay, if there are no external forces, I should have said that. Then the impulses are equal and opposite. It just follows from what we've done here, which is fairly straightforward. So the total momentum, P1 plus P2, is unchanged. Since the change in momentum is the change in this one plus a change in this one, and the two changes are equal and opposite, then P1 plus P2 has to be constant. It's unchanged. Okay, a simple example of how we can apply this. This chalk isn't writing very well. Or maybe it's me. Simple example. Let's say we've got 2 kilograms here. Moving at 5 meters per second. And 3 kilograms here, moving at -4 meters per second. Okay, now this is before collision. And after collision, we find that this 3 kilogram object is moving to the right at 3 meters per second. And this 2 kilogram object is moving to the left with some velocity. True. I should have noticed what notation your book uses for the velocities before and after. I do kind of remember. I think I do remember. A little different than the notation the text has used in the past, and maybe different than the notation of the printed text. I don't have the current edition of the printed text. Okay, so I'm going to call this velocity V1B for the velocity of the first object before, and I'm going to call this 2 kilograms M1. So here's V1B. And here's V2B. And of course the 3 kilograms is M2. After the collision, the 3 meters per second we're going to call V2A. And you're going to say V1A equals what? Well, it's pretty easy to answer the question. Momentum before collision, and I'm not going to bother putting arrows over this. I'm just going to use plus and minus signs to indicate directions. When we do a collision in 2 dimensions, as we'll do in a minute, we'll modify this. But we'll use the arrows, or we'll use X and Y components. But right now, just going to go with plain old P1, with the convention that if P1's positive, the momentum is in this direction. If it's negative, it's in this direction. Think I direction, if you wish. Okay, so P1 equals the momentum. Let's say P1 before equals M1 B1 V1B equals 2 kilograms times 5 meters per second. So that's 10 kilogram meters per second. V2B, P2B is 3 kilograms times negative 4 meters per second. That's negative 12 meters per second. Negative 12 kilogram meters per second. P2B is M2 V2B which is 3 kilograms times negative 4 meters per second. And what am I doing? I'm doing P2B again. I want to do P1 after. Looked at this and wrote down something that just wasn't necessary. Okay, so P1 after is M1 V1 after, and P2 after is 3 kilograms times 3 meters per second. Nine kilogram meters per second. So P before, which means total momentum before. I could put P total before, but I was going to use P sub B for the total momentum before. Has to equal total momentum after. Total momentum before is 10 kilogram meters per second minus 12 kilogram meters per second. And that equals total momentum after, which is M1 V1A plus 9 kilogram meters per second. Well, what we're after is V1A. The only thing we don't know, we know M1, so we can solve for V1A. This is going to give us negative 2 kilogram meters per second. Add negative 9, you're going to have negative 11 kilogram meters per second. M1 is 2 kilograms. So you're going to get negative 11 meters per second over 2 kilograms. And you're going to get negative 5.5 meters per second. Now there's another question that arises. What about kinetic energy? Well, you can calculate the kinetic energy after collision, and there are two possibilities. One, your kinetic energy is less than or equal to the original kinetic energy. Another is that your kinetic energy afterwards is greater than your original kinetic energy. Okay, if the kinetic energy afterwards is greater than the original kinetic energy, then you have to ask, well, where did the extra energy come from? Because these balls, the motion of these balls, the kinetic energy of these balls is less than it before is less than it was after. So the kinetic total kinetic energy is increasing, means something's got to be doing work. So this is not an isolated system, in other words. Could be that there's a spring mechanism in one of these balls. Okay, and when they collide it's triggered and adds energy. All kinds of things could happen. But the kinetic energy afterwards, if there is no other source of energy. If there's no source of potential energy, can't be greater than it was beforehand. It can be less. Two balls smushed together, they could come to rest. There'd be no kinetic energy. If they smush together and stick together, the kinetic energy will be less than it was beforehand. Okay. Now in symbols, because that's the way we really want to look at this, you got M1, V1A, plus M2, V2A, and actually I should probably put the before. I'm going to change that A to a really sloppy B. Yeah, it could be written this way. And then you identify the variables you know, this one, this one, this one, and all your masses. And you choose your target variable, the one variable that you can solve this equation for. You can solve it symbolically and plug stuff in. In a simple case like this, where you can really pretty much understand what the quantities mean at every step, I still like to look at what the quantities are because I get more insight that way, but I don't want to just have that insight. I also want to have the insight of how these equations go together. The danger of writing out an equation like this and write it out correctly, like this is an A, not a B. Danger of writing this out is you start using it as a formula without thinking about what it means. Then you lose insight. Every time you do a problem, you sacrifice the possibility that problem will increase your insight and you just get an answer. You don't want to do that. Okay, well, that's a typical collision in one dimension with fairly straightforward conditions.